In this lesson, we have introduced you to some of the Hall of Famers, discrete probability distributions for modeling out discrete random variables, continuous probability distributions for modeling out continuous random variables. And a question that you can ask is, oh yeah, that's so cool. I'm glad that there are these Hall of Fame probability distributions in both families, but what if I want to make my own? Am I stuck always picking out one of these Hall of Famers? And while you will frequently use one of the Hall of Famers, we're just going to quickly walk you through like the basic rules for doing a discrete probability distribution and also for a continuous probability distribution. The discrete version is pretty basic. It's not so bad. You just create the events that are of interest to you. You assign a random variable to the events. So my random variable is a payout, and if the roulette ball lands black, then it payout 200. If it lands red, 0. If it lands either 0 or double 0, then the payout is 0. And I have assigned a probability mass function. My probability mass function can never have a value below 0. It can never have a value above 1 or 100%. And the sum of all my values must equal 100%. As long as those rules hold, I have a legal discrete probability distribution. It's great that I have access to my Hall of Famers like the Poisson or the binomial or the geometric, but I don't need them. Let's take a look at the continuous. Now, we've introduced you to the exponential distribution, the uniform distribution, as well as the normal distribution. You can make your own continuous probability distribution, model out a continuous random variable. Later on, we'll show you a second version how to do something like this, but let's just get started here. And I have some phenomenon. My random variable can somehow take legal values between -5 and 5. It can take any of those values, -5 to 5. And for whatever reason, I happen to believe that y equals x squared minus 5x models out the probability. I have to really follow two rules. As long as I follow these two rules, I'm in the clear. Now remember, I said that my continuous random variable x could take on any value between -5 and 5. One of the two rules is that this curve can never go negative. See, so like between x equals 0 and x equals 5, my parabola, my curve, goes negative. So what I can do is I can cheat here a little bit. I can look and find the minimum value, and it looks like my minimum value is hit when x equals 2.5 and the corresponding y value is -6.25. So let me fix the first problem. It's pretty easy. What I'm going to do is just add 6.25. I could add more than 6.25, okay? The whole thing is I cannot add less than 6.25. So for instance, if I wanted to add 7, no big deal. That's fine. But we'll just make it 6.25 to see how this plays out. Now, here's the second issue. The total area under my curve for the legal values that random variable x can take has to be 1, the area under the function. This function goes on forever and ever and ever, and it gets big in a big old hurry. And so here's how I do this. I take this function and I say int, so that's for integral. This is where the calculus comes in. Remember, my random variable x takes on legal values between -5 and +5, and then I'm going to treat this like a probability density function, a PDF. We'll get there before too long. I'm just going to put parentheses for good measure here, and then I'm going to write dx. Desmos tells me that the area under the curve for this parabola between -5 and 5, the total area under the curve is 145.833333. So what I can do is I can just copy, and then out in front of the integral, I can put 1 divided by 145.83333, and look, the area under the curve is 1. So this value that you're looking at here, this is a legal PDF. I mean, really the PDF shouldn't include the integral. It should just be, get rid of this, and there you go. So that's a PDF, x squared minus 5x plus 6.25, all divided by 145.833333. That right there follows all the rules of a legal continuous probability distribution. We made it homemade.